Alright, good morning. Welcome to Wednesday of week 8. So what's happening? I guess one thing I'd like to say yet again is assignment 1 was due Monday. I'm worried there are still a few people that haven't submitted it. The late penalty, you certainly can't get 100%, 90%, even 80% today for the assignment, but you can still get some marks if you submit what you've done today. So you may be disappointed with what you've done on the assignment. You may only think it's worth 50%. We'll see what we think it's worth, but definitely submit whatever you've got if you haven't submitted something now. Alright, that's assignment 1. Assignment 2, yesterday wasn't a good day. I was hoping to have assignment 2 released for today, and I have to apologize. One of the problems is actually my fault. I made some, so Jashank has been busy working on the assignment for quite a while, and I decided that some things needed to be made. I changed my mind. I decided that some things needed to be made simpler. Particularly, that I'm worried that people won't start the assignment or struggle to get started on the assignment. So I wanted to make a few things about the assignment simpler, which has slowed things down a bit. I'll talk about assignment 1 shortly, but you won't be able to start on the assignment. I'm hoping tomorrow, but Friday at the latest you'll be able to start working on assignment 1, and I'll come back to talk about the assignment in Tuesday's lectures. What else is happening? We have our usual labs and tutes, which are focused on file operations and particularly relevant to the assignment. So you'll want to do this week's labs and tutes before you try starting on the assignment anyway. On weekly tests, so as usual there's a weekly test that's due tonight at 9 o'clock, so please make sure you've done that, and there'll be another weekly test popping out very soon, due in a week's time. So I think that's where we are with the course. Dylan, is there anything else of general interest I should be mentioning?
I don't think so for the moment. I think that's all good.
Alright, okay. Let me then, I think I'll introduce the assignment, and then we'll go on to, we're going to talk about files, file metadata, file operations, creating directories, maybe creating symbolic links and that sort of thing in the lecture today. But let me switch to, there we go. Oh no, let me flip screens. Let me get to where I want to work. I've got a spot set up to work. I'm changing the wrong screen. Alright, I think in this directory I've fetched the files for the assignment. Let me repeat, you can't get these files. No, I've fetched some files related to the assignment here. There's some extra files there, which in fact I'll remove them now, and I was playing around with this before the lecture, but there are some crucial files here for the assignment. Alright, the first one is, we give you a file called examples.zip for the assignment. So I wanted to talk about first what a zip file is. Examples.zip. There's a wonderful Unix program I can ask it. It'll tell me what that is. Zip archive data. At least one in a version for it. It's an archive. So zip is one archive format. What's an archive? An archive is a way of bundling together one or more files and perhaps file-like objects together into a single file. So I'd say you bundle together files or directories or other file-like objects in a single file, and you may include metadata about them, such as file permissions. So other information is also included in the bundle. So examples.zip is an example of such a bundle. It's a single file of 91,235 bytes, but in it is the information stored about many more files. How many more? Well, we can explode examples.zip using unzip, and it's exploded it there. How many files did it extract? It had So examples.zip has information about 208 files and directories inside it. So it's an archive file that's storing the information about 208 files and directories. Why do I like archive files? Why do we pretty much all use archive files? Why? Convenience. It gives us a convenient way to transport a group of files as one unit. So attach it to an email, back it up, give it to students for an assignment, make it available via a web link. So it's a convenient way to provide to capture all the information for a group of files in a single file. There are other benefits. One is compression. If I'm looking to save space, compressing a group of files is better than compressing each file individually. Why is that? Compression works by finding common patterns and representing them in a more compact way. So if you imagine I've got 10,000 C files, there's going to be a lot of common patterns there, common C code. So if I put them into an archive file and then compress it, I may save a lot more space than if I just compress them individually. There are other reasons there, but that's another classic reason to use an archive file. Alright, so zip. Zip is just one example of an archive file format, and there are a number of programs that handle that format. They don't have to be called zip, and there are many implementations of programs that will manipulate archive files in that format, either create them, give you information about them, or extract the files from them. Are there other archive? Yeah.
One thing that zip does is that zip is both an archiver and a compression. They don't have to be the same. There are some programs that are only archivers, there are some programs that are only compressors. Zip does both, but it not necessarily has to.
That's a good point. Yeah, so sometimes they're kept more separate, and it's actually better if they're kept more separate. So other archive formats. A really popular one on Unix-like systems is called TAR, T-A-R, which actually, the T stands for tape. I think it's a format that used to be used for backups. Well, maybe it still is used for backups to magnetic tape, but it's widely used to distribute files on Unix-like systems. And there is also compression available, but it's sort of independent of the archive format. There are a number of other archive formats out there. On my system here, there's probably 5 or 6 different archive formats supported for special uses. Actually, probably more. How does this all relate to the assignment? The assignment is to do your own archive format. Well, the assignment's going to specify an archive format, and you're going to write code that creates archive files, prints the contents of archive files, and extracts the files from archive files. The archives are going to have specified formats. So let me show you about it. All right. So there's a nice thing about this assignment. For those of you who did COMP1521 2 terms ago or more with Mark Chi, we decided to name the archive program after Mark's cat, a very popular feature in COMP151 lectures when Mark was teaching. Mark's Chi's cat was called Chicken, so our archive program is called Chicken. And
well,
the archive.
I'm hoping it still is. We don't really want past tense there.
And the archive format will be an egg. So chicken will produce eggs, which I thought was funny. You probably won't, but that's okay. All right. Let me show you how it's. Well, let me mention that something else. You're saying, oh, this is all very confusing. We're going to give you a detailed description of this and give you tools for understanding this. So, and this will be generally useful in understanding file formats generally and working with complicated formats generally. But one thing you'll have for the assignment is a reference implementation. So I guess you had a reference implementation for the first assignment. It was in C, and you had to do it in assembler. This one you've got a reference implementation, but you won't be able to see the source. But you will be able to say 1521 chicken and do what the archive program is supposed to do. So let's try it out. Let's create a file. We'll create two files. So I've created two files. I'm going to use the reference implementation of chicken to create an archive file. What do we call it? From those two files. So you will be writing code to do this. Don't panic. Well, actually, this is subset 3 of the assignment, so definitely don't panic. Some parts of the assignment starts out easier and gets into more and more interesting, challenging, and difficult things. But there, a file called a.egg has been created, and it contains all the information about hello.txt and by.txt. Chicken has a list option which can say what's in an archive, so we can ask it, and it'll say, oh, it's got two files in it, hello.txt and by.txt. Yes, sorry for Jay, who had me for a COMP1521 lecturer, and no chicken, no cat at all, really. I apologise. Chicken also has a different listing option, capital L, which tells you more information about the files. It tells you the permissions, the size, and the file name. So they're the two listing operations for chicken. You're saying, I'm now going to remove hello.txt and by.txt, so they're gone. But I can get them back from the archive, so I can say to chicken, extract the files that are in the archive, and they'll be back again as good as they ever were. So we hopefully have the same files back again. All right, now some students may be asking, the question that people would, well, it's something I'd be asking is, look, can I use whatever format I like inside a.egg? As long as my create code works and my extract codes works, can I use whatever format I like in a.egg? No. We're specifying the format you've got to use, and you've got to follow that format and that format only. There's a couple of reasons for that, but a big one is that a lot of students aren't going to get all the parts of chicken working. It's a pretty challenging assignment, and you're getting to a HD by the time you're doing all the extracting stuff, all the creating stuff in full. So if you write code that works with egg files we create, we can test your listing code and give you marks for that. We can test your long listing code and give you marks for that. So we can give you eggs and give you marks according to that, or we can get you to create eggs and then check that. So you have to follow the format for the egg files, the specified format. Right. So I guess then the question that, well, first, you're saying, do I have to do all of this? No, we're going to give you argument processing code and just set you up so you've got to write 3 functions. So we're going to do some of the assignment for you. I'm going to put it in a file called chickenmain.c, which you don't change. It has the main for the program. You just leave it alone, and it calls 3 functions in chicken.c that you have to write. There's also a file called chicken.h, that communicates between that both of those files include. That's how you do model file programs. So let's have a quick look at chicken.c and see what the gaps you're going to fill in. You can't get this file yet. I'm not sure it's exactly right. There's nothing worse than giving out a file to the whole class and then discovering 3 hours later that something needs to be changed, and then everyone's confused and it creates lots of problems. Alright, here's the first of the functions that you'll be writing in assignment 1. It's list egg. It'll be given the path name of an egg file like a.egg, and you'll have to print out what the files there were that were stored in a.egg. At the moment it's just got some sort of debug printfs there. Leave those there for a while, but eventually you want to delete them. It also has an argument long listing. If it's non-zero, then you have to do the longer listing, which we saw. Actually, I'll show you. That's a good point. Am I in the right directory? Yes, I am. So if I say little l, like that, 1521, there we go. Then this program will be given, a.egg, and then it has to print out hello, bye, and text there. Because it's a dash little l, this will be 0. The same function will be called for a long listing, but this will be 1, and you'll have to print out more information. So you'll have to look at a.egg. You're saying, well, what am I going to do? You're going to be doing fopen, you're going to be doing fget, so you're going to be fopening egg path name, you're going to fgetc, you're going to be looking inside egg path name to do this. So the very first call here is going to be an fopen, and then some fgetcs and some ifs saying, if I see this byte, print this, if I see those bytes, print that. Just implementing this function gets you a decent mark for the assignment. Gets you up above a pass. The next function is extract egg. Just call with one path name, which will be an egg, and your job is to get all the files out of the egg. Yeah. So we'll give you an example of that again with a.egg. If I say this, the code over in chicken main.c that you don't have to write, we'll call extract egg, giving it the path name a.egg, and you'll have to do the work here, which the printing out the 2 lines. Sure, that's easy. Creating the files is a bit harder. No, that's not too bad. And the last of the 3 functions you have to write is create egg, and it's a more complicated function. This is for students who want a distinction or better in the assignment. There's some debug printfs there which you'll eventually delete. I'd leave them in until you finish in debugging, or just comment them out as you debug. They're quite useful as debug printfs. But you're told to create an egg, and you're given the files to put in the egg, or I should say files or directories. We'll see that a bit more shortly. But and 2 arguments here. I don't want to talk about this too much because that's further on in the assignment. So I'm mostly worried about people getting in and getting started on the assignment. I'm worried about people getting list egg working. So by the time you've got list egg and extract egg working, create egg should make a lot more sense. So let me emphasize, these are the functions you write over. If I look at chicken.h, it says don't change this file and some other stuff, but it says these 3 functions are in chicken.c. Oh, and it's got some other useful they're not quite hash defines, but they're equivalent to hash defines. It's got some useful constants. So the constants defined in a slightly different way that we're used to, which you may wish to use. They're useful defines for you. They relate to the format, which we're going to talk much more about on Tuesday, perhaps. Ooh, and there's even an egglet format. What do you know? All right. Now, so yeah, you don't write main. You don't have to figure out how to detect -L or -X. There's actually a bit more complexity with that I won't talk about until next Tuesday. With subset 3 sort of things. Now, let's suppose we wanted to reverse engineer an egg format. You've heard the word reverse engineer, I'm sure. What does it mean? It means that there's a created object, typically binary, or a created interface, a created API that the maker of hasn't disclosed, and we'd like to know how it works to use it. So we'd like to reverse engineer what the egg format is. Can we do that? Well, by some strange coincidence, in this week's lab, you create a program called print bytes. So print bytes is handy for looking at binary files. It's an amazing coincidence. It's in this week's lab, and it's showing me what's in a.egg. Interesting. All right, I'm going to reverse engineer. Maybe I should start with something really simple. So let's make a 1-byte file. So I'll make a file with 1 byte in it, and I'll use the reference implementation to create an egg containing just 1 file. And I'll specify the -C option to do the create.
Someone asked, maybe you could try opening a .egg in a text editor. I wouldn't recommend it because it is a binary file, which may not be great. Most text editors will probably warn you, if not outright refuse to open it, but it certainly would not look nice to read.
Look, let's live dangerously here. Let's see what VI does with it. Oh well, it's not too bad, but it's not very enlightening. Yeah, there are editors, binary editors, but let's have a look now with print bytes at simple.
Yeah, VI is going to be one of a few editors that just don't warn you in any way and will just allow you to do that. Most graphical editors will also pop up a warning telling you it's a binary file.
All right. So when we're reverse engineering, you look for certain things. So we're seeing 2 bytes here, C8. They were in the other egg as well, so they seem to be a constant, and that's actually true. The C, the 0x63, is actually the first byte on every. We'll call them egglets. So every egglet, which is the unit for storing a file, starts with the byte 0x63, which is an ASCII C for chicken. The next byte can have a couple of values, but until you get to the later stages of the assignment, it's just going to be 8-bit. Sorry, 8. There's actually 3 formats: 8-bit, 7-bit, and 6-bits for egglets, and that byte specifies the egglet format. So if you're looking for a distinction or better, you'll have to handle 7-bit and 6-bit formats. But the first part of the assignment, you can assume that's just 8. So those two, that byte tells us what format we've got the contents of the file in. You can guess what they are. They're the file permissions. Apparently has an ASCII string. Alright. Now we've got a bit of a puzzle for you. It's nice, isn't it? If print bytes just printed out the byte values, it'd be a bit hard to understand the file. But print bytes also tells you what it is if it's an ASCII character. So it tells you 0x74 and says, well, if it's ASCII, that's a T. And that works quite well here for decoding that, because we can see there in the egglet is the file name. That then leaves us guessing what that is. Anyone got any guesses what that is? 17. How many bytes are there? 17. So apparently those 2 bytes tell us how long the file name is. If we look down here, we can see the file contents. That's the file contents there. How would I know that? I'd have to look at other eggs. So I could do that. I mean, I could do print bytes of another egg, of a more complicated egg. And if you look there, there's the contents there on a more complicated egg. What are these 6 bytes? If you work through it, you could eventually figure out those 6 bytes tell you the length here, the length of the file contents, which then tells you how big a file you can put in an egglet. It's 6 bytes, which is 6 times 8, or 2 to the 48. So the maximum file size is 2 to the 48. Is that okay? Yeah, I think that's probably big enough. Alright, I thought that was nice just to show you could decode this format. It would be a more challenging assignment. It's not a very good assignment because the first student, sort of a few students work really hard and discover the format, then they tell everyone else, and everyone else has got it easy. So unfortunately we can't make it a sort of a reverse engineering assignment. So the assignment spec will describe exactly what's in eggs and what they look like. But that's given you a taste of it. Now, there is a different program which I've showed you already, which is actually a much more powerful program if we have a binary file and want to look at it. So that is XXD. We'll run it on the simple egg. And it's doing well. It is more powerful. It's a bit more. It's set up to handling larger files. It's a bit more industrial strength than print bytes. Though honestly, it's doing pretty much the same job. So it's showing you what's inside the contents of the egg. So let's go back to what your mission will be. List egg. You've got the path name, you'll open the file, then you'll have to get byte by byte and do things with it. Figure out which is the path name printed out for the short listing. If it's a long listing, you need to get the permissions and print them out. You need to get the length of the contents of the file, print that out. Then you need to print the file name and print it out. So it's not that hard. Extract egg's a bit more interesting. There you'll be creating files. So you'll open this file and read through it and discover, it contains b.txt, and you'll have to create b.txt and so on. Alright. So I think we're going to leave it there. We're going to come back. I'm going to release the spec. I'm hoping tomorrow, but if things don't go well, and this hasn't been a good week at all, it may be Friday, which will have the remaining code, and my usual advice with assignments would apply. We love people who dive in early, but people who dive in early and start the assignments typically discover minor mistakes we've made, well, hopefully minor mistakes we've made, which has to be fixed. So if you are one of the people who dive in early, expect to have to get updated copies of various files and so on. So hopefully everything will be stabilized by early next week, and in Tuesday's lecture I'll talk more about the assignment and give you hints on getting started on it. So we might, in Tuesday's lecture, we might actually we might put a bit of code in listegg and play with it and see how we do. So that will be your assignment: writing your own file chicken, your own file archiver. Yeah, Ariane's asking, we only get 2 weeks for the assignment. This is the joy of 10-week terms, I'm afraid. So with this week's lab is just working through the crucial stuff for the assignment. So after this week's labs, you're really just ready to start on the assignment, I think. I'm hoping that if you're at a loose end the next couple of days, maybe you got maths to work on, physics, something like that.
I also believe we're going to put the due date on Monday of week 11, Monday 9 a.m. week 11. Is that correct?
That will be the due date of the assignment. Will be Monday of. So you'll get 3 weekends if you like to work on the assignment, plus if you do most of your assignment work on weekends. And no, I can't extend the assignment date. Oh, that shouldn't be up. And I can't extend the assignment date any further because StuVac is reserved for exam preparation. All right. So let's change what we're talking about. Let's go back to looking at file operations and cover some of the file operations we need to do for the assignment. Now, on screen is the second last example from yesterday. You'll remember I really like this example. Let me emphasize, well, there's one thing that's missing from this example. It's missing a lot of error checking. So it doesn't check the fopen succeeds. It's not checking these operations. But apart from that, it's a beautiful example of quite complicated file operations, but all sensible ones. So I'd encourage you to understand this as this is treating a file, as I'd say, as random access, moving about a file, changing just 1 byte of a file. So it's a good example. I encourage you to look at that. I mention this because then after this we went to the sparse file. That was if you found that interesting, great. If you found it confusing and scary, you can just ignore it. But this example, this sort of captures everything we wanted to show about file operations changing a file. So that was quite a nice example. So let's move on from there. Okay, that was the one we looked at. That one up. All right. So we've seen general versions of these stereo operations. It's worth mentioning, just for clarity, there are specialized versions for convenience. So there's fprintf to printf to a stream, but because 99% of printfs is to standard output, there's a short version which is printf without saying the stream, which goes to standard output. Similarly for scanf, so there's a shortened version that goes there. For puts to print out a string, there's a shortened version of fputs. Even for fgetC and fputC, there are shortened versions. There is one that I really have to mention. Well, I guess that its time is dying. It's decades of warning students never to use this function. Gets is an infamous function which reads a string. The trouble is, reads a line. The trouble is, it and reads a line from standard input. But unlike fgets, you don't pass a third argument indicating the size of the array you're reading into. I've never actually found out why or who made this mistake. Maybe no one wants to own up to it. A mistake made long ago. It was an endless source of security holes. The problem being, it let attackers do buffer overflows, which we saw when we looked at the stack. So you never use gets, but it was a case of bad design. There's just no good thing you can do here. You just got you can't pass an infinite array, and it doesn't take a length anyway. So gets is an example of a function we'd never use.
It was created in conjunction with getC, and no one stopped to think. It was when they were designing the original standard library. It was just more of a pattern kind of thing. We have getC, we need getS, and they didn't really stop to think about the ramifications of what they were doing. And yeah, one of the worst functions in the C standard library, which now is deprecated, officially deprecated. So now not only is it a security hole to use it, it's also incorrect, which is good.
I would say, by the way, the people doing buffer overflow attacks exploiting this were about a decade in the future or more when this function was added. So perhaps I'm being a little unfair about the people who put it in the C library. But I mention it because there's another fantastic function called snprintf. I mentioned it. I think I mentioned it. I've mentioned it in a couple of lectures. It's one of my favorite C functions, snprintf. It has a sibling function, sprintf, and for some reason people don't fear sprintf enough. Sprintf is evil. Sprintf is just as bad as, well, it's actually that's not true. It's not quite as bad as gets, but it should not be used. So sprintf doesn't have a way of parsing the array size, but snprintf does. You give it a char array and a size, and then you can then use it like printf. So it's printf into an array. You want to be a power C programmer, snprintf, enormously useful. You often don't even think about it in C programming. The first time I often think about snprintf is I think, oh, I've got this Python that does X, I need to translate it into Y. And then I think, how can I do that in C? That's a bit tricky. Then I realize a few snprintfs and away I go. scanf can sort of be useful as well. It's scan from a char array. I don't like. You may have heard me say I don't like scanf. Using fgets plus scanf can give you better results than just using scanf. Yeah, but anyway, worth mentioning for your programming toolbox. All right. Now we get to a more interesting function. All right, we get to a function called stat. It's not part of standard I/O, so it's not portable. But it's enormously useful. I think if there are systems that are sort of Unix-like, they will often emulate stat because it's such a useful function. What does stat do? It gives you the metadata for a path name. So you give it a file name, hello.txt, and it gives you back metadata for the file. How does it do that? Well, it's an interesting interface. You give it a pointer to a struct, and it fills in the struct for you. So you give it a pointer to this struct here, saying, "Oh, here's a space to put all this information." And what will it give you? It'll give you the inode number for the file. You remember that just like you've got a ZID, every UNSW student has a unique ZID. Every file on a Unix-like file system has a unique inode number. Do you need to know that? Yeah. it can occasionally be useful, but you have to be doing sort of pretty clever programming for it to be useful. It'll tell you the type of the file. Is it a file? Is it a directory? Is it a symbolic link? And way back, was it 3 lectures ago, I talked about this Unix philosophy of everything being a file, and so how there were other things that looked like files that did weird things, like the one I showed you, I think, was if I wanted to know what CPU I'm running. There's something that looks like a file, but when you go to look at its contents, the operating system instead looks at what CPU it's got and says, oh, this is what's... So that file, it doesn't really exist. The operating system you request it tells you what CPU is there. And another one we showed you was dev random, except I can't cat it because it's binary, which if you look in it, you just get random numbers. But they're being generated by the operating system. Huh. Alright. There are a couple of sibling functions to stat, but that's not important. Here is the struct. Now, it looks more confusing and scary than it is. So, these are all integer types. Yeah, we get to get absolute portability. Remember, Unix runs on everything. To get this absolute portability, you have to parameterize this. You have to define particular types for this, particular types for that. But you can imagine all of those being int, and that's close to the mark. So there are 10 numbers there, plus 3 times, and times are stored in a separate struct. Interestingly, there is the size of the file, the user ID and group ID, who owns the file, how many links there are, the permissions stored in a special way. Alright. Okay. This is the ST mode field. What's this? I'd call it a bit mask. An array of bits. So it's all of these Boolean variables. This bit is set if other people can execute the file. This bit is set if people can write the file. Generally not something you want, have everyone able to write your file. That's set if everyone can read your file. Same for group, which we'll just gloss over. Same for you. This bit's set if the file is a FIFO, or whatever that is, a character device. Oh, that one's set if it's a directory. That's actually relevant to the assignment, and a regular file. I should note for the assignment that your file archiver, Chicken, just deals with regular files and directories. That you'll be given a big assumptions section that say you can assume this, you can assume that. One of the things it'll say is you can just assume you only have to handle regular files and directories are for people looking for distinctions or better. But so those bits can tell you that information. So that's all stored in this one number you get back from st_mode. I think I'm almost ready to try this out, and you will have seen I've got prepared code. Yeah. So let's try out this function, see what it looks like. Alright. So what have I got? I got a main function. Calls for every argument it's given, calls this function. prints out a message. I create one of these stat structs to hold all the metadata about the file. I call the stat function. Yeah, that might get you into a problem in some languages. It's a separate namespace. You can have a struct stat and a function stat. That's okay in C. Is it okay? Is it? You can do it. Should you do it? I'm less clear about it. But it is what it is, I guess. If it fails, we use the p-error message to print an error message. Otherwise, we just do a few printfs of the information. Let's see if that all works for us. So let's clear that off. That's scaring me. There we go. Oh, right. So it does for every file we're given. So let's get information about ourselves. Let me repeat. If you're experimenting with file operations, more than one student I've seen, far more than one student have been thinking, oh, I'll write a program that removes a file, and now I'll test it on my program, and oh wait, I've just removed my program. It's very easy to accidentally destroy the stuff you're working on, so be careful here. So, out of all of this, that's the information we've got back from stat. They're supposedly the file permissions, 644. And we should be able to see those on stat.c. I wonder if I could see those change. If I'll change, I'll get rid of group and read permissions from the I'll make it so the file is only accessible to myself. That's right, the daemon that copies it to the website, the web server sees that and puts it back again. Whoops. Well, but we can still that will give us a different mode there anyway. You can see now that's changed to a 0. So those 3 permissions become that octal digit. Those 3 permissions become that octal digit. Those 3 permissions become that octal digit. You think about it, octal digit, 3 bits. What do I want to say? I want to say read, write, and execute. Those 3 possibilities. Can the file be read? Can it be written? Can it be executed? They're encoded. Now, yeah, Hamish is mentioning, but that's a bit seems a bit weird, doesn't it? The information about what type of file it is mashed together in the same number. Who thought that was a good idea? Systems people do tend to try and save space. So in the file metadata here, we've got what will be, I think that will be a 16-bit number. So they're saying, well, I only need 9 bits for the permissions. Let's shove another. Let's use the other 7 bits for something else. And here's the other bits getting used. So if it's a regular file, it's a 1 there. Right, let's create a directory. I've created a directory, yep. Let's stat that. Note my use of, by the way, of LD with a directory to say don't give me the contents of the directory, just give me the information about the directory. But if I'm looking here, 755. Yep, that fits. Those permissions there become the 5. Those permissions there become the 5. These permissions here become the 7. And the 4 up here, that means a directory. And there it is in the chart there. So that's using stat. Getting this file size out might be useful for the assignment. Right. Now, I guess one thing I have to mention is, how do I store a time? So with a file, we want to store a couple of times. We want to store time of last access, time of last modification, and time of last status change. The assignment doesn't involve these, and I don't think we'll do any. Oh, yeah, maybe we do. We'll use them in a lab exercise, perhaps. Yeah, it's possible we'll use them in a lab exercise. But how would you store a time? Turns out the classic way to store times in computer systems is just in absolute number of seconds since some point in time. So Unix-like systems appeared in the 1970s, so they picked as what people would call the epoch, their time zero, if you like, January the midnight, January the 1st, 1970. So if you're 1 second into 1970, the time will be 1. How many seconds has it been since 1970? About that many, apparently. So we just store set times as an absolute count of seconds since this. Now, times are complicated things, which I don't really have. We don't have the opportunity to go into here. And the next thing you might be saying, well, time where? And then if you talk to astronomers, then they'll raise even more interesting questions about time. But let's just say it's universal coordinated time, and then we can compare files independent of time zones. Alright, but I guess the more 1521 thing here is the metadata. We're storing when the file was last accessed, when the file was last modified, and a slightly different thing was when the file was last status changed, which might be the time the permissions last changed, for example. So some information's there. You're thinking, I can't remember all of that. No, this is all stuff where we'd look up recipes if we had to access, and that's absolutely fine. That's a normal programmer thing to do. You're saying, how do I get the last modification time? You'd look online and get a little bit of code that someone had written showing, giving an example of how to pull the last modification time out of a struct stat. All right, that's using stat to get the metadata of a file, and that could be useful for the assignment, because you might want to grab out the file size, and you might want to decide if the file is a directory or not. So you might want to look and see if the file is a directory or not. I think they're the two things I could see that would be useful for the assignment. Oh, forgot. Yes, when you get to subset 3, you'll need to get the permissions of the file from there as well. Yeah. So when you get to subset 3, that the information in that field, that will be useful. So those two things are useful for the assignment: size and mode. The rest, not relevant. Interesting though, very interesting. Let's go to my next example to have something simpler before we take a break.
A more advanced archiving tool will try to keep all of those fields consistent throughout an archive. So something like zip will actually have in it a way to store all the times and permissions and even the owner, and it will try to keep those consistent when you extract a file again. Of course, sometimes that's not possible. If you extract a file on a system where the owner doesn't exist, that won't happen. But it is stored in a zip file, the original owner of the file, or at least their ID.
So there are two excellent points there. One is, three excellent points. One is the archive format for the assignment is a bit simpler than typical because you can't store things like file owner. But that's actually quite useful if you want to archive a whole computer system. You might have files owned by Dylan, files owned by me, files owned by Zach, and you'd want to remember that. And if you restore them, you might put them back to the same owner. But actually, modification times and things like that can actually be really useful metadata. If I'm looking at a source project, it's actually really useful to know, oh, well, that file hasn't been changed for 3 years, or this file was changed yesterday. So being able to capture that and restore that is also enormously useful. Not part of the assignment, but
I remember
useful.
a court case that was someone almost got jailed for evidence tampering because a file modification time had been changed, and what had happened was the file had been uploaded to Dropbox with a server in a different country, and the timestamps had been modified due to the time zone issues, and then someone thought the file had been modified after they said it had been, and a whole legal thing came of not maintaining file metadata as correctly as it should have been.
So if it gets really important, by the way, files aren't necessarily the best place to keep file modification times aren't the best place to keep this information, and a software repository system would keep it separately. I was going to mention one other point that Dylan made there. If you transport a file archive, and that's pretty common, to, for example, give students a zip file, and they'll work create it on Unix, and they'll work on Windows. It's quite possible that Windows won't have some of the features. They won't have the particular permissions, or you might not have groups or something like that. So if you go cross-platforms, some of the things may not be representable on the other platform. So it's not possible to exactly replicate. One fun fact would be there are file names that are legal on Unix and not legal on Windows, and vice versa. So, all right, I was going to talk about McDear before the break, but we'll come back to some easier programs after the break, and then some more complicated programs. So after that sort of working through stat, let's take a 5-minute break. Stand up, stretch, go and do something for 5 minutes. Alright, everyone, welcome back. To repeat, we'll be coming back to the... a couple of key messages. One, you can't start the assignment yet. We'll put up an announcement when the assignment's out and the starter code ready for you to go and use. Hopefully tomorrow, but things haven't been going well. If not Friday, though. On Tuesday's lecture, I'll go through the assignment in more detail, and I'll show you some example code in the first function. So we'll write a little bit of code, and I'll talk more about the complicated parts of the assignment as well. Now, we worked through stat, sort of a ugly, I would say, function to get metadata about a file, which you might use for the assignment. And we'll show you some prettier, easier to use functions perhaps for the assignment. Here's a nice one, mkdir. So I want to create a directory. What the system call I guess I use to create a file is open, or from standard IO fopen to create a file. A directory is such a different thing that there's a different system call to create a directory, and hence a different wrapper function for it. That function is mkdir. And basically, you say mkdir and the directory you want to create. You also, second argument, permissions. Permissions as an octal number. Well, the permissions are interpreted as an octal number. You can supply the number how you like, calculate the number how you like. But if you're a good programmer, you'll probably write it as an octal number in C. Remembering C has this weird thing that you can put, you say a number's octal by putting a leading 0 in front of it. We had a discussion about this. Python went to something like this. In Python you'd write it as 0 and a little o for octal, 755. Is that superior? Yes, I think everyone agrees. Superior, sadly. And well, C, I think we discussed, we'll get it in C23 or C25 or something like that. But it's also, by the way, a common source of bugs, particularly with people who don't just do regular programming, never have to think about octal. They'll say, Andrew, my program's not working, and it's behaving really weirdly, and I'll look, oh, you've left a 0 in the front of that number, and that's being interpreted as octal. And I'll go, what? Who does that? Anyway, C does that.
Unfortunately, that's not going to be fixed, because for backwards compatibility, they're not removing the old syntax, they're just adding a new additional syntax. So typos will still break your program.
Let me also say, though, if you're a sort of person like me and learn all of this stuff and understand it, there are people out there who will happily have you, give you interesting, well-paid jobs to be the person on the team who can solve that problem for the team. So if you're finding this stuff, it's maybe not been good, but knowing it can be useful. If we create a directory, it's not it's empty, sort of. It has two special entries in there initially. Every directory has an entry for dot, which is a reference to itself, and a reference to double dot, which is a reference to its parent directory. mkdir returns 0 is successful, otherwise it returns -1. Important to know, I guess. Yeah, that's one thing you're always looking for in manual entries, isn't it? Let me go to this screen. If I say man mkdir, number one thing I really care about is return. I guess this is worth. All right, let me take a breath. Something's gone wrong here, and it's important to note what. So I've said man mkdir, and I haven't got the information I want. Why? The problem is there is a program called mkdir you can run on the command line. There's also a C library function called mkdir, which you can call from in your C program. There are manual entries for both. I've said man mkdir, I'm getting the manual entry for the wrong one. You're saying, shouldn't they have just given them different names to make my life easier? Yeah, maybe, I don't know, but it's too late for that now. So there is a way out of this. If I say man 1 mkdir, I get information about the command line program if I say man, I think it's 3 mkdir. No, it's man 2 mkdir.
This also happens for stat, printf, and many other functions. So putting the number in is almost always useful.
You're smart. You'll figure it out. I've got great confidence in you all. All right. So that's the information about mukdir. And again, when we look at manual entries, we don't panic because there's weird things like mukdir at that we really don't know what they do. We try to go on to, oh, what have I just done? That's what I've done. Let's throw it back again. What we're looking for often in these manual entries is what it returns, and it's telling me. Surely it should tell me somewhere. There. All right, crucial thing. Why do I say that? Why am I emphasizing this? Because students often think about true and false, but mukdir returns 0, which is false, interpreted as a C value, and -1, which will be interpreted as true, and that's pretty common for system functions. So yeah, always think about what the system function returns. Look it up. Don't write if mukdir blindly. I hear you say, well, what do I write? Well, there you go. There's a good example of some code saying if mukdir not equal to 0, print out the error. Let's try this out. So let's compile it. Let's say a.out. Let's create a directory called Penelope. Can I spell Penelope? I can, I think. A directory called Penelope has been created. We can even see the dot entries if I say, I think it's the -a to ls. So it's showing me the files in Penelope, the dot and the double dot. But often I just want to see the data for Penelope itself. That's really what the D entry in IS is, isn't it? So I'm saying stat Penelope and give me the information for Penelope. Give me, well, you can see that's the ls must be looking at that mode field. Here are the owners coming back. Here's the file size. What does a file size mean for a directory? Yeah, not much. Here's the modification time. What does that mean for a directory? That's an interesting one. That's often quite useful. And there's the name of the directory. So you can see ls is actually running, it was probably doing a pile of stat calls. Or one stat call here. So I've made Penelope. What happens if I tried to make Penelope again? Oh, look at that, I get an error. So I can't recreate the directory because it already exists, and that's that P error there printing out this, and I've said it's about that, so that P error is printed, oh, I'm printing out something about Penelope, and then it'll look what the error was, and the error was something called file exists. Yes, not very clear, is it? One thing I wanted to show you is if you try to create a file named Fred/Mary, that won't work because Fred doesn't exist. But I could create Fred and then Fred/Mary, and now there's a directory called, there are now directories called Fred/Mark. There you go. I probably used to Mary. And fumble fingering again. So if you give mukdir a long path name, if you want to create a tree of directories, you have to start at the top and create them one by one. That may be relevant to the assignment as well. Oh, that's mukdir in operation. A special system call, creating a directory, permissions. I think that's nice. So that's a happy program, easy to easy enough to understand. And yes, you will be calling mukdir in the assignment, but it hopefully won't cause you problems. But check its results and check it properly. Yeah,
that's,
I think
that late subset 3 as well. You won't be calling mekdir early on in the assignment.
No, it's a I'm heading for a HD, something I have to do. I would caution you one thing. I've seen this a few times where you ask students to create directories. They say, "Oh, my program's got this really weird bug. Maybe the compiler's broken." And then you say, well, but wait, you're calling mukdir there and not checking the result. Are you sure it works? And they say, yes, yes, yes. Well, you still put an if statement there and check and print something if it fails. And they go, oh, the mukdir is failing. Oh, that's what's wrong. So check every call you do. Don't be that person. Alright, so that was the good news. This is a bit badder news. Badder? Worse. Getting the contents of a directory. So what are the contents of a directory? Essentially, it's iNumber and names. So it tells you the group of files and also tells you their iNumber. You probably don't care about their iNumber, but it tells you anyway. So there are special system calls to access a directory. It hasn't always been that way, but it is. It's not. It's an interesting part of system design. Yeah, if I'd said to you, what do you think the system calls will be like? You might not have expected this. So the wrappers for them are an equivalent to open called opendir, an equivalent called readdir, which gives me information about one file, and an equivalent to close called closedir. So that will give me the contents of a directory. Let me list this directory. Oh, look at that. It's just listed the contents of this directory. I could make it clearer by saying give it the whole directory name rather than dot, but this should be the same. Okay. The good news and the bad news. The bad news is, to complete the assignment, you need to use opendir and readdir. The good news is it's well into subset 3, so you can get up to distinction level, I think, in the assignment without using these functions. But you will have to use them. One thing I'd say is that how you access a directory, you don't expect it to be anything like this necessarily on other platforms. It's an unusual API and not necessarily replicated. The other thing you'd notice here is directories aren't kept in any particular order. You might have expected the contents to be sorted. I've seen many programmers fall there. And it's a bit weird because you had dots down here and double dots way down there. Why, how did that happen? But there we are, getting the contents of a directory. Now, imagine your LS.
Well, it is sorted. It's sorted by inodes.
It's sorted by inodes. Oh, I had not. Is it sorted by inodes? What about double dot?
Oh, actually, no, it's not. It's almost sorted by inodes.
Almost sorted by, yes.
Oh god, it's even worse.
Yes. Imagine your LS. You might run code like this to get the contents of the directory, and then what you might do is call stat to look at what each of these is. Are these files? Are these directories? Get more information about them. So you can imagine yourself as LS doing opendir, readdir, stat, and things like that, and you can get all the information you need. That's quite pretty. All right. Let's see. You're saying, well, are there other functions I need to know about? Yes, there are. Why? I guess there's a few reasons I want to show you these. There's sort of a shallow, immediate pragmatism. Oh, you need some of these to do the assignment. Actually, yeah, you only need chmod to do the assignment. The others you don't need to do the assignment. There's sort of a utility. Is maybe you want to write code that uses these, and it's not very portable, but I also like you to have seen the shape of these sort of operations. So even if you finish up Windows programming, you've learned something about these operations, and even though you have to learn about the Windows equivalent, you get a feeling for how an operating system works, what sort of things it does. So let's have a look at a few of these other ways of manipulating file-like objects. What's next on the agenda? I think next on the agenda really should be set file permissions. Yeah, chmod. So I want to do my own chmod program. So I've got, what have we got? We've got I've got fuzz.c. I want other people, well, I want to be able to say, I'll get my own chmod program, which I'll call my chmod. Now, the real chmod takes a variety of arguments. I've just set this one up to just take an octal number, so I'll give it an octal number. I'll say my chmod 444 fuzz.c, and has it done the job for me? Look at that. So it's made the permissions read-only for even the owner of the file. So now I can't change fuzz.c. So I can try to overwrite fuzz.c, and it won't do it. I can go into VI and say write fuzz.c, and it won't do it. How did that work? There's one nice thing here. This 444 is not 444 decimal. It has to be 444 octal, which is 4 times 64 plus 4 times 8 plus 4. What does that work out as? That's, well, you can work that out. How did that conversion happen? There's no converting code there. The str_L function, it's quite neat. You can give it a base there. Say, convert this string to a number, to a long, and use that base. Cute. And here, str_L lets you do error checking. So this is actually, is that attractive code? No, not really. But that's a way of checking whether str_L will work there. Alright, you can just ignore that if you're worried by that. Otherwise, we come down here and we chmod every file to that mode, and that's it. Chmod is the built-in function, path name, octal mode. So we can set permissions our own way. So I can say man2 chmod and find out about the C function, and there we go. Telling me mainly stuff I don't want to know. Oops. I'm not sure what happened there. Now, you might think the function the system called a remover file would be called remove. It's actually called unlink. Why? Because files are actually held in place in the file system by most files are held in place by one link, and you remove it and the file's gone. But a file potentially is linked in many places in the file system. So unlink doesn't remove the file, it just removes one link to it, and if there's another link, the file survives. So you're saying, what the hell are you talking about, Andrew? Let me show you then. Let me create a file called andrew.txt, and I'll create a link to it as...
To be even more confusing, there is a program called rm which we usually use to remove a file. There's also a program called unlink, which does the same thing, just with a different name.
Alright, so I've created a file. In fact, I'll make 3 links to a file. So there is one file, but it appears 3 times in the file system. There we go. So it appears in the file system, 4 times. How would I manage that? I must have made a misspelling. Now I'm confused. Oh no, it's I've listed it twice in the LS. I'm not having a good day. So there are 3 links to the file's been given 3 names. It appears in 3 different. It appears 3 times in the directory listing.
You can use ls-i to show inode numbers, and they'll all be the same.
Or I could use my own program, list directory, which will also show the inode numbers the same. So this is showing link to andrewt.txt. Oh, that's inode number this finishing in 30. Second link to andrew.txt. That's that finishing in 30. And where was andrew.txt and all of that? There it is, same I number. So there's really only one file. It's like if UNSW would let you have 3 different names. So you had one ZID, but UNSW lets you go by 3, 4, 5, 10, 50 different official names, which would be sort of confusing, I guess. But it would emphasize why we have ZIDs, in this case why we have I numbers, to uniquely identify the file. The end result though is if I remove andrew.txt, it'll be gone, but the file's still there as second link to andrew.txt and link to andrew.txt. I have to remove all the names of the file before the file itself goes. If I did this now, the file will be finally gone. Interesting. A little scary, but interesting. So that was unlink in operation. Here's a unlink's not hard to use. Be careful. Here's an enormously useful function. Oh no, sorry, not getting to what I want. This is change directory. This one's really stupid. There's an important point here, a very important point. So every program has associated with it at any point in time a current working directory. If you'd like your running program to have a different working directory, you can call chudir and say, I want my working directory now to be this path name. So I've used that to try and make my own CD function for using here in the shell, and it won't work. So if I go cd/temp pwd, if I go cd back to where I was, that works. Let's try the mycd function I've written. Say change to the /temp directory. It does nothing. Why? The working directory is a property only of the running program. So doing a chudir affects this program until it exits. Doesn't affect the program that ran it. It doesn't affect other programs running at the same time. It only affects this program. The current working directory is a property of the running program. What's happening here then? When I do pwd, I'm actually obtaining the working directory of the shell I'm talking to. So it does me no good to do the chudir here in a program I run. I have to do a chudir in the shell. You're saying, well, Andrew, how does the CD program work? Answer, it's not a program. the shell intercepts the CD and does its own chudir. Yeah. That's a little. Don't freak out. That doesn't make sense. If it made sense, great. If it didn't, don't worry about it. This is a program I'm hoping will make sense. So this is trying out CD, trying to do multiple CDs. So let's try it out and run it. So the program said, what's my current working directory, using the get CWD program. It had to give it a buffer to put that in. It's an interesting question about how big we make that buffer. There's often not a good answer for that. There's a constant called pathmax, which may or may not work. So I've used that. So I've said, tell me my current directory. If you can't, I don't know why you'd be unable to get your current directory, but print out an error message, which it hasn't. So then I've printed out my current working directory. If my current working directory is /, my program stops. But otherwise it calls chudir to double dot. So it goes up the directory tree and goes round again. And here you can see it in action. It prints says, oh, I'm in this directory. Oh look, now this directory, this directory, this directory, this directory, this directory, finishing up at the top. So it climbs the file system tree. So we have a little program that walks round the file system tree using chudir to change its working directory and get its working directory.
The man page says an interesting error case is it will return an error if the current working directory has been unlinked.
Ah, I know, yeah, that happens regularly, so yeah, I should have thought of that. Right.
Also, the maximum path depends on the file system that you're using, so that's another reason why pathmax is a really weird constant to have, because it's not a constant.
I don't know what's just happened there. Hurry. We're going to get to the program I thought I was getting to, which is rename. Give a file a new name. Why do I think this is such a useful function to know? You're thinking, well, Andrew, I could just copy the file and remove the old file. There's two reasons why rename is much better. Rename, there's more than two reasons. Rename is efficient. Rename just changes the name. It doesn't move the file's contents about. The file's contents is 30 bytes, doesn't matter. The file's contents is 30 terabytes. You'll find a rename will save you a lot of time. That's one part of the story. It preserves modification times, other metadata. It just changes the name. It's efficient. What else? It's essentially atomic. What do I mean by that? I mean, if we've got other things happening, I might be concerned there's an intermediate state in the changing of names that will break other things. So the old name might exist and the new name might exist, or there might be a time when neither exists. So there might be this awkward time when other programs will break because of this renaming. And generally it's guaranteed that this won't happen. Either the old name will exist or the new name will exist, but not both. And so we can rely on there not being these awkward transitions. And a lot of system programming relies on these sort of properties to do some things safely. Otherwise, rename's really easy to use. I'm just mentioning it, these useful properties. Let's try it out. We've got that program. What do we want to rename? Oh, we'll rename my CD. Oh, actually, no, what do we call it? We'll rename the to broken program. There we go. And that should change the name of my CD to broken program. And the first one should be gone, and the second one should be called broken program. There we go. But let's just emphasize that the metadata doesn't change. So we'll put it back as mycd. And the modify time should be unchanged. Yeah. Whereas if I'd used open and copy, and those things would have changed. So giving a file a new name, a very useful thing to have in your armory. Let's move along. What more have we got to see? Oh. Alright. Is this a good program? I'm not sure. But this program is testing limits. And yeah, I've certainly noticed students who experiment with code are the ones that succeed generally. So this is sort of trying to be in that vein of I've seen these new functions, let's try them out. So this one tries to make a weird directory structure. So what does it do? It's got a counter that's running from 0 to 1,000. Every time round the loop, let's reason about it, does one mkdir, one chdir, one get current working directory. So it's a program that creates 1,000 directories. Okay, yep, sure. It's using snprintf to get the directory name. And the directory name is pretty dull. It's D number. So it creates D0, D1, D2, D3, up to D999. After it creates the directory, it changes working directory into there and then gets the current working directory and prints it out. So it should create each directory inside the last. Alright, so it should nest the directories if I've got my code right. Haven't tested this, but it looks good code. I'm running it. We'll pipe its output to more to see what happens. And it's making, well, we can make our window wider. And we'll start again. Oh, doesn't handle the directory already existing. Oh, actually. So you're asking, how do I do rename from a shell? Move is what is the command line program that does a rename. So I've renamed that. I could have just removed it, but. And now this program is building up something 1,000 levels deep. Is there a good reason for this? Not that I can think of. I can never think why you'd nest directories like this down. Occasionally you create a few directories. Right, let's run it.
Unless you're doing some QA on a program and needed to stress test it.
Yes.
Like, for example, there is a path max, which this may very well be nearly getting to.
There we go. So it's created that directory. So yeah, we might do this to stress test our things. Oh, stress test what? We might do this to stress test our assignment implementation to see if you can add a directory that's 1,000 levels deep. I'm CDing into that directory. Oh, and CD won't go there. That's sad. That really is sad. I'm a bit surprised about that. You disappoint me, CD. Alright, so let's just go a couple of hundred levels down. And there we are, a few hundred levels down. Look at that. I'm now 300 directory levels down. I can type cd double dot 300 times to get out. Or I can cheat and go straight out with an absolute path. And we're back to where we wanted to be. That was sort of weird and fun. That's actually a nice example. it's hard to come up with much use for this sort of coding, but it's a beautiful example of using all three functions: change directory, make directory, get working directory. It's a nice example of all of them. I'm happy with that. Try that one out. I'm not sure what's happened there. This is another one of
Andrew,
this.
Do you mind deleting all of those before they get arsynced?
All right, just for you. They probably have to, they are being asynced right as we speak. But it's now asyncing the delete. I must remember not to do that in the
and the old as well, I believe.
I think I got that one as well already. Yeah, I did.
Oh, good.
All right, a different program for you. This one makes a symbolic link. Oh, that just makes a regular link. Sorry, just a regular link using the link system call. Where are we up to there? Let's show you just do. Alright, so I'll be a bit nicer this time. I'll make a temporary directory. You'll want to do this for a lot of stuff for the assignment once you start extracting files. You'll want to create a temporary directory, change into it, and then maybe run your chicken program from one level up to extract some files in this temporary directory. What I'm going to do is I'm going to compile the mini links program from one level up and run it and see what it does. So what's it done? It's created a file called hello.txt, but it's given it 1,000 names, 1,001 names. So this directory seems to have 1,000 files in it, but they're actually all different names for the one file. And LSS here is saying you've got 1,001 links to this file. So I can sit here typing rm 1,000 times and I'll still have one link left to this file. How would I know that? Well, Dylan mentioned ls-i to tell me inode numbers, and it's saying this file has that I number. So you can see they're all the same file. Or I could use the program we wrote, list directory, which does something similar, which says these are all the a couple of things to note. One is unordered, the other is same I number. So I've given the same file multiple names. I should take a step back here, and you're saying, well, but why would you do this? You don't do this very often. It's a fundamental thing at the very shape of file systems, that a file may have multiple names, but then it's not actually something we exploit very often. It's a pretty rare thing to deliberately give a file multiple names. We've seen it, deduplication is the classic use, which we mentioned. Oh, do we have one to do symlinks? Chain links. Wait a minute. Yeah, we should have one to do symlinks. Last example.
Just so you know, Andrew, rsync is recursive, so a temporary directory inside live still gets synced.
I'm happy for that.
So there are currently 1,000 files being rsynced.
Shouldn't take it very long at all. I've removed the temporary directory, and now actually I need it back again though. It's going to confuse the rsync, but anyway. Alright, so there's a different sort of link, a very different sort of link, which is a symbolic link. So this is something we use all the time. It's like a referral. You look at file, you ask for file A, and you get told no, go to file B. And it's possible you can go to file B and get another symlink which says go to file C. And it's possible you might end up following a file a couple of times. Why would we do that? It's often very useful to present different names for files or directories. It's enormously useful for putting together sort of namespaces. It's something we do all the time. Let me show you it in simple use first.
It's probably helpful to immediately mention that if you've ever used shortcuts on Windows, symbolic links on Unix systems are basically the exact equivalent. So if you know what a shortcut on Windows is, this is what this is that we're looking at.
And let me be very clear here that it's the other way around. That Windows is mimicking Linux here with its shortcuts.
And
yes,
also,
an excellent
also
point, Zach.
importantly, it's conceptually, in practice, they're implemented very differently.
Oh, I didn't need to know that.
Conceptually, it is the same idea.
All right, so thank you both. So that's a good point. So yeah, shortcuts. That's a good way to think about them, and the Windows people have thought about how can they explain this to people, perhaps not as familiar with file systems as us. So yeah, that they do very much the same job, though in the end the underlying semantics are quite different. So I've created a file called hello.txt. And I just might need to have it available by another name, so I can say if anyone asks for Ola.txt, send them to hello.txt. What does that look like in ls? Let me make that wider. So here's the symbolic link, and it says, oh look, I'm called A, but I really am a reference to B. So ls writes a little arrow saying you asked for A, we really want A, go to B, and you'll get hello.txt. And lots of programs just follow such symbolic links quietly for you without doing anything. There are exceptions, mainly things that are specialist programs. So ls will just tell you, no, you have to go to hello.txt. Actually, if you want another analogy, for those of you who know your HTTP codes, a symbolic link is like is it a 302?
Well, most threes.
Most
means
threes.
redirect, so pretty much any 3 is a redirect somewhere.
So if that helps you, it's like a HTTP redirect, if you like. All right. What happens though if I create another symbolic link that says, look, if you ask for selmat.txt, take that to ola.txt. Oh, wait a minute. I've got the arguments around the wrong way. It's the name of the link you're creating comes last, which I regularly forget. So make that go to selmat.txt. So now if someone asks for selmat.txt, they get hello. And there's 2 levels of referral there. So if I ask for this file, I get told, oh, I'll go to that one. I ask for that, and that one says, oh, I'll go to this one. I finish up here. Now you're saying, can I have? Is there unlimited levels of this? Well, I've got a program to find out how many levels the operating system will let you happily follow. How many levels of indirection you can create. But before we do that, I'll just excuse me for a second. Sorry, I just needed to sneeze. Before we do that, let me show you something. If I remove hello.txt, file's gone. The symbolic links don't keep the file in place. They don't connect it into the file system. They're just referrals. Now I get a weird thing. if I cat cellmat.txt, I'll get it won't be found, even though it's there, but it points to something which points to something which doesn't exist. So you follow the symbolic link chain and you end up referred to something that doesn't exist. So that's symbolic links. Enormously useful, really useful things to use. So the previous links, sometimes called hard links, connecting a file properly at multiple places in the file system, rarely used, but important to understand if you really want a deep understanding of how a Unix-like file system works. Symbolic links just used all the time, and their equivalents if you're working on other systems also used all the time. Windows shortcuts get used all the time, as from my very limited knowledge of Windows.
There was a question in the chat, which is, what is the practical difference between a hard link and a symbolic link? One of the main ones is you can't hard link a directory. You can symbolic link a directory. A directory cannot be hard linked. But for a file, there's not that much difference. Practically speaking.
You can't hard link across file systems. Otherwise, the other thing as well. But hard links are this very real thing that gives a file two names in the file system, and can't be done for directories or special objects or can they be done for can they be done for devices?
I don't think so.
I don't actually know. Whereas symbolic links, give you this referral. Can be to another directory. Often is. Typically, that's one of the big uses of symbolic links, is to link them to another directory, and can be go anywhere. So I've written a program I have written that creates a little file containing "Hello Andrew." Easy code, nice code. You're saying, Andrew, that's so nice compared to the stuff you've been showing me. Then what does it do? It then tries to create symbolic links to that file, and then if that works, it then tries to create another symbolic link back to the first symbolic links. It tries to create this gigantic chain of symbolic links that each returning in turn to the other, finishing up at the file. And then it wants to check they work, so it's opening each symbolic link and seeing if it gets the same thing from the symbolic link as it got when it read the original file. All right, so this is sort of a sort of an advanced sort of example. The individual operations aren't hard, but what's happening there is a little weird. Where are we? We're in the temperature. Oh, well, it's not going to stop. It's still going to be arsynced, isn't it? So what are we going to do? We're going to compile chainlinks.c and run it. So it managed to make 40 symbolic links before the operating system said, no, that's not going to work. Let me expand just to look at this in all its glory. So there was hello.txt, and I said, oh look, hello0.txt links to hello.txt. I said hello1.txt links to hello0.txt, and I kept doing that. And we got as far as here. I can look at that one. Oh no, it stops. So the operating system will happily follow through 39 levels of symbolic links. So it'll look at hello.39.txt and go to hello38.txt. It'll look at hello38.txt and see, oh, that refers to hello37.txt, and follow it all the way through until it gets to the original file, but its limit is 40. Why do you think it has a limit? Why? Because it gives it an easy way of terminating if there's a loop in the symbolic links. I'm trying to think why there isn't a better solution to that, why it doesn't just check for repetition, but I don't know why that is. But I can't think why you'd want to follow 40 levels of symbolic links for a real purpose. I've seen situations where you finish up following maybe 5 symbolic links or 6 symbolic links, and sometimes in setups, in complicated file system setups. Why does it? So first character here is what sort of thing it is. We've seen dash there, I think, for a regular file. We've seen D there. L means symbolic link. what about the permissions? Well, symbolic links don't have permissions as such. They just point to something. So the eventual object you finish up with will have permissions, but the permissions on a symbolic link don't matter. So they just lead you to where you're going. So yeah, it doesn't make any sense to have permissions, so you see them as that. Alright. Oh, that's not a bad point to stop. Alright, I hope at least some of that has helped you understand this. So to repeat, we'll try and get the assignment out for tomorrow. I'll be back talking about it on Tuesday, but I'm hoping with what I've told you so far and the spec we release and the other stuff, it'll help you to start on the assignment. If you're struggling to get started on the assignment, don't panic. On Tuesday, we'll write a little bit of code in the list egg function and see how we go there. But thank you for tuning in, and see you on Tuesday. There'll be an announcement when we release the assignment.